Hey everyone, this is our lesson on flow of energy, and by the end of this lesson, you should be able to infer simple calorimetric calculations based on the concepts of heat loss equals heat gained and specific heat. We're really going to focus on that specific heat portion here today. But before you get started, you may want to review your energy units way back from Unit 1. They're also on your reference packet, the ones that you'll need. So let's first make sure we can just remember and understand what energy is. So energy, we know, is the movement of your particles in most cases. Look at it with temperature, things like that. And when we're looking at a reaction itself, there are two parts we need to look at. The first is the system, and the system is the part of the reaction you're focusing on. So it's the actual reaction itself. The other part is the surroundings, and that's everything except for the system. So that's the beaker the reaction is occurring in. That's the countertop it's sitting on. That's your hand holding the beaker. Everything outside of that reaction is considered a surrounding. And then when we look at a reaction and we're looking at this change, we have to make sure to apply the law of conservation of energy, which states that it's neither created nor destroyed. It's only transferred from one place to another. So we cannot make energy out of nowhere. We can't lose it to just nothing, right? It can move from one place to another, though. So your heat of your system, which is noted by the letter Q, the heat of your system is going to be equal to the negative heat of your surroundings. So if your system gained heat, your surroundings had to have lost heat to the system. So heat lost is equal to heat gained. Then two terms you need to know to describe how energy is flowing is endothermic and exothermic. So endothermic heat flows into the system. So think into. And then exothermic heat is flowing out of the system. So it's exiting the system. So there are three calculations to really focus on here. The first one is specific heat, and this is probably the most important one for you to understand. You will see a little bit of the other two, but specific heat's the big one. And specific heat is defined as the amount of energy or joules needed to raise 1 gram of a substance by 1 degree Celsius. So your units will be joules per gram degree Celsius. Oh, and I think that's actually defined a little bit quirky. So your calculation, which is on your reference packet, is that C is equal to Q divided by M delta T. A lot of times, though, especially if we're given an element that's on your reference packet, you're going to be solving for Q because C, the specific heat is an intensive property. It's something that doesn't change based on that sample. So a lot of times you'll solve for it as Q is equal to MC delta T. I like to tell people if you plan on going to medical school, you have to take the MCAT, and this is your MCAT formula, which we will use in a minute. Then you have heat of fusion and heat of vaporization. For both of these, we are looking at a phase change. And when you have a phase change occurring, there is no temperature change. Okay, so all of the energy that's going into the system is being used to break or make bonds. Okay, in these cases, it's to break bonds. So you don't actually see a temperature change occur. Since there is no temperature change, we can't have degrees Celsius in the unit. So heat of fusion is to go from solid to liquid. Heat of vaporization is from liquid to gas. Both of these have a unit of joules per gram. So we only care about mass and energy. So again, a lot of these you will probably solve for the Q here because the heat of fusion, heat of vaporization is a constant value for those specific samples. And these will be on your reference packet. Pay attention to, it does depend sometimes on the state that you're dealing with. Because some of these values can change, whether that be specific heat or heat of fusion or heat of vaporization based on what state you're looking at. So now let's do an example together. So let's use orange. What is the specific heat of an unknown substance if a 2.50 gram sample releases 6 joules of energy and its temp changes from 25 to 20 degrees Celsius? So we've got a 2.5 gram sample. It releases 6 joules of energy and a temperature change here We want to know the specific heat, which is C. When you get into these problems, start underlining, circling, and labeling now. So grams we know is a mass. J is your energy, so Q. And then your change here for delta T. So delta T, we would do final minus the initial, so 20 minus 25, which means we've got negative 5 degrees Celsius. So our formula here, since we're looking for C is equal to Q divided by M delta T. Our Q was 6 joules. Ooh, 6 joules. We're dividing that by 2.50 grams times negative 5 degrees Celsius. None of my units cancel, and it's going to leave you in joules per gram degree Celsius, which is what you want. So we will do 6. Let me turn it this way. 6 divided by 2.5 times 5, which would be 0.48 joules per gram degree Celsius. Okay, so it's pretty easy to do as long as you label, underline, and circle in your problem. Okay, so it's not too bad. And you can even have your negative here, but since this is a constant value, you'll, get rid of that negative for our change. Okay, so if you want to, you can think about change as like the absolute value of this, which would make that positive 5. So there is just a quick look at those. Make sure everything is in the right unit that you need. Sometimes I could try to trick you and tell you you have calories instead of joules. If I do that, you've got to convert to joules. Or I'll give you Kelvin instead of Celsius. You've got to do that. I'll give you kilograms instead of grams. You've got to make sure they're all in the right units. So now let's talk a little bit about calorimetry. And calorimetry is the process of measuring the amount of heat absorbed or released during a chemical reaction. So you mix two things together, you've measured the temperature originally, you mix two things together, you measure the temperature again, and you see how much heat has flowed into or out of the system. And in some cases, like this one that we see over here, this picture right there, is called a bomb calorimeter because you actually will set a sample on fire. Oops. In that little box right there, that box heats up the water. This thing will spin around to kind of like make the water move around and flow, and then you'll see the temperature change from there. So you measure the change in temperature of water, and then you will calculate the Q of water, so the heat of water. Usually water is going to be gaining heat here. So the heat of water is equal to the negative heat of the metal, because remember, Q gained is equal to Q lost. So whatever the water gained, it had to gain from somewhere, and that would be the metal. And now that you know the Q of the metal, you can use that to solve for the specific heat of the metal. So a lot of times this will be like, this unknown was given. It gave off, it caused water's temperature to raise from this to this. What is the specific heat of the metal? Okay. And that's what you're going to be doing in this one. So you're going to do this one, but I am going to help you just label everything. Make sure you know what you're looking at. So we've got a 38.61 gram sample of a metal. So this will be the M of the metal. Is heated in boiling water to a temperature of 100 degrees Celsius. So this is T1 of the metal. Okay. In a calorimeter that contained 80 milliliters of water, remember this is equal to 80 grams because 1 milliliter is equal to 1 gram. And that's the mass of the water at 54 degrees Celsius. So this is the T1 of water, or T initial. The temperature goes up to 61.0, so that's T2 of water. Calculate the specific heat of the metal, so we want C of M. Okay, so remember, you're going to first find the Q of the water. Then remember that the Q of the water is equal to the Q of the metal. And then find the C of the metal using the Q of the metal that you solved for already. Okay, so those are the steps, but I want you to try to solve it out. So pause.